Thanks for watching this video. This video is about Bayesian decision between simple hypotheses. We are still using the same reference book, Empirical Bayes Methods, second edition. This lesson is about session 1.4. This is a session about Bayes decision between k simple hypotheses. Let us start with the case with two simple hypotheses first. Here, we have two simple hypotheses. H1, the parameter lambda is equal to lambda 1. The second hypothesis is parameter lambda equal to lambda 2. In particular, lambda 1 is smaller than lambda 2. And then the posterior probabilities, lambda equal to lambda 1, the probability is equal to theta 1. And similarly for lambda 2. Then here is a simple graph which illustrates the prior cumulative probability distribution. And we see that there is a probability mass of theta 1 at the value of lambda 1. And then up to lambda 2, there is a jump to g lambda equal to 1 at the value of lambda 2. Okay. This is a simple decision problem with two hypotheses, so the analysis will not be too difficult. Let's try to derive what is the decision function delta x. First, delta x is defined in terms of a partition of the sample space into two regions, A1 and A2. In particular, what I mean is when x is in region A1, then H1 is accepted. And similarly for H2, the loss function for this decision problem is defined as follows. L is equal to 0 if the decision is correct and equal to 1 otherwise. That means the decision is wrong. Then we can write down the corresponding base width. The base width consists of two terms, and I highlight the important thing in red color. First, remember it is the cost of making wrong decision. So you will see that in the first term, the first term represents the event where lambda equal to lambda 1. So it is equal to theta 1 times the total probability of x when the true lambda is lambda 1. Okay? But what is the range of x that we are summing over? We are summing x in region 2 because it is the cause of making mistake. That means the true lambda is lambda 1, but it turns out that x is in region 2. So we make mistake. The second term, the interpretation is similar. If it happens that lambda is equal to lambda 2, but sadly x is in region 1, we make mistake. So it is equal to theta 2 times the total probability when x is in region 1. Okay? So these are the two terms in the base width. Then let's try to analyze how to construct these two regions, A1 and A2. Let's think about the following situation, and let us consider the words in blue color first. For any given x, if I put x in region 1, then what is the cause of mistake? The cause of mistake is the probability of getting this particular value of x, and also lambda is in fact in lambda 2, right? And so the corresponding probability, that means the cause of mistake, is theta 2 times fx conditional on lambda 2. And similarly, if we put x in region 2, A2, the cause of mistake is theta 1 times fx conditional on lambda 1, which is the probability of the value x and lambda equal to lambda 1. Okay. And then we want to specify things in terms of posterior probability. And surely before talking about that, just we make a decision with lower cost, right? So essentially, when the cost of putting in region A is lower than we put it in region A, and if the cost of region 2 is lower than we put it in region 2. And then now we try to express everything in terms of posterior probability. So now let's consider the orange color words. Let us divide these two probability by the marginal probability. Okay. In the denominator, they are the marginal probability. Okay, just divided by the same term. And then, so we can make the following conclusion. We should put x in region I. That means we accept or choose hi if hi has higher posterior probability. And also, because we have only two hypotheses, right? These two posterior probability will be add up to be 1. So it is a very simple conclusion. We accept hi if the posterior probability is larger than 1/2. Okay, so this is a simple conclusion from the case where I have only two hypotheses. But in fact, this general conclusion, I mean, we choose the hypothesis with higher posterior probability is a general conclusion for K hypothesis. Okay, let's continue. And also, in previous analysis, I do not say anything about the shape of region A and A1 and A2, right? They may not be a simple interval. They may be union of many interval or consist of many points. I did not say anything, right? I did not prove anything. Here is a case where we know that region A and region 2 is a very nice partition of the sample space into two intervals. When will this happen? This happen when the likelihood function have some kinds of monotonicity. And in particular, what I mean is fx conditional on lambda 1 over fx conditional on lambda 2 is monotonic in x. In particular, here I illustrate a situation where it is monotonically decreasing. And then I also plot this graph theta 1 times fx conditional on lambda 1 over theta 2 times fx conditional on lambda 2. It is monotonically decreasing. And according to the previous conclusion, we know that there will be a point where they are exactly equal to 1, right? And then the corresponding value of x is c here. And this c will be exactly the cutoff point. Will be exactly the cutoff point, which cut the whole sample space into two intervals, A1 and A2, divided here. Very simple. And then the last point here is just a remark. In fact, we can derive the value of C by simple calculus. Surely under the assumption that we know A1 and A2 are two simple intervals. Okay, and here let me assume that the sample space of X is the whole real line from negative infinity to plus infinity. Under this situation, the base width function can be represented in these two integrals. Okay, and then let's try to differentiate the base width with respect to C. here is the result, and then we set it equal to 0, and then the cutoff point of these two interval C will be defined by this equation. Okay, and in fact the first term theta 1 f z conditional on lambda 1, representing the marginal benefit of setting C slightly higher. And then the second term is representing the marginal cost of setting the cutoff point a little bit higher. Okay, so in fact the analysis is related to what I said before about how to define A1 and A2. Okay, this is very simple. Let's try to extend the analysis to K simple hypothesis. The situation is very similar. The only difference is now we have K hypothesis. We have Xj. Xj is the hypothesis where lambda equal to lambda j and j equal to 1, 2, 3, dot, 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 k. And I label lambda 1, lambda 2 up to lambda k in the order of their size. In particular, lambda k is the largest. Similarly, each of them has the posterior probability theta j, and all these theta add up to be 1. Okay, very simple. And let me define the region of accepting hypothesis j, denote it by aj. Okay, then the corresponding base width is defined as follow. The idea is very similar. The terms in the parentheses representing the cost of making mistake. Okay, so for example here, suppose it turns out that the true parameter is lambda I, red color in red color, and then we make mistake when the true lambda is not lambda I, right? So that's why in the summation inside the parentheses, it is a summation of j without I. Okay, we sum j from 1 to k except equal to I. Okay, and theta j times the integral here is the total probability of making mistake. Okay, then we use the similar logic, very similar in fact, similar logic to think about how to construct all the region A1, A2, A3, so on and so forth. And here, just for illustrative purpose, I just say that I just talk about A1, but in fact all the reasoning are similar. Suppose we try to put X in A1, okay? Then what is the cost of making mistake? So then the cost of making mistake is theta 2 times this fx conditional on lambda 2 plus dot 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 up to theta k times fx conditional on lambda k. Okay, this is the cost. This is the cost. And then I define the marginal density or marginal probability. Okay, and then we calculate the posterior density. Okay, similarly, we put x in the region where the cost is lowest, right? Okay, then the posterior probability of lambda equal to lambda 1 conditional on x is equal to this term theta 1 times fx conditional on lambda 1 over fx. It is exactly equal to 1 minus cos. Okay, so we can have the following very simple conclusion. Because the analysis is totally symmetry for all j. Okay, so therefore we know that we accept or choose hypothesis j if it has the highest posterior probability. Okay, So it is a simple discussion of Bayes decision with k simple hypotheses.